Welcome to another episode of Complete Developer Podcast, the podcast by coders for coders about all aspects of creating your best life as a developer.
I'm Will, the accomplished developer, author, and software architect.
And I'm Beej, the journeyman developer sharing my journey in development.
Complete Developer Podcast is supported by listeners like you. We are now on Patreon at www.patreon.com/Complete Developer Podcast.
The Raspberry Pi came out in 2012 and revolutionized the IT industry. The small yet powerful boards allow for building inexpensive IoT solutions, emulators, and even cluster computers. The latter allows the use of several Raspberry Pi nodes to work together to quickly solve problems that would take a single Raspberry Pi board a long time. In this episode, we talk about my school project where I built a cluster computer from Raspberry 4 Model B nodes. We'll talk about cluster computing, testing the cluster that I built, the results, and some lessons I learned along the way. But before we get started, Will, what's been clustering you this week?
Well, we were in the middle of a pretty solid refactoring session where we touched almost 100 files. And the error channel blew up. So that was a wee bit of stress. Apparently, some of the network connections are required going into the main building. Even though most of our stuff is on the cloud, there is some stuff that has to call back in. And it turns out that those are a lot more important than I thought they were. Because when that connection's not there, pretty well just falls over. So that was rather amusing. While I wasn't on the support team this week, the thing about it is that Teams errors messages also stack up. And so I lost the whole right side of one of my monitors because the Teams messages just kept going. Yeah. And it's super stressful because you're like, okay, are we about to get interrupted to go look at this? Because the way it was exploding looked like an all hands on deck. Fortunately, it wasn't. So pretty thankful for that. I don't know that I really have a whole lot of other news because it's only been 2 days since we recorded last.
Yeah. So I got an A in my parallel programming class. Woot woot. Got a 15 out of 15 or a 100% for those of you who can't do percentages in your head like that on my paper. I missed one question on the final. One question. And the only reason I missed it is because I completely misread the question. And it's so funny because I answered it correctly based on what I thought the question was. And the professor, he was like, I want to give you points on this, but I can't because it is absolutely the wrong answer. And I can tell it's just because you misread the question. But, I didn't answer what the question the way he had written it. And he's like, I think he might have given me partial credit if I needed it, but I missed one question. So on the whole final, not that big a deal. But it actually had to do with implementing MPI send and MPI receive in OpenMPI. So it was funny that happened to be the question I missed because I misread part of it. But looking forward to getting to use my camera this weekend. Since COVID, I haven't gotten to be a photographer at church because they've needed me on the tech team more than the media team. I mean, I've gotten to use the video cameras, but not my photo camera, photography camera. I don't know. You know what I'm saying? Anyway, we're having a photo shoot at church on Friday. So I'm getting to use my camera again. Amanda used it Mother's Day for church photos. But again, I was actually leading the production team on Mother's Day. So that was kind of cool. Our team lead was there. She was just sort of stepping back and observing, and then actually got to, take a little break and relax some, which I'm glad because, she's doesn't do that very often. So that was good. Speaking of relaxing, I haven't gotten to do that yet, though I am going to take some downtime on Saturday while Amanda is out of town on a girls' trip. Though I'm leading the tech team at church, since our team lead is also going to be on that trip, that's only going to be a few hours. And so the rest of the time, I'm going to probably end up cleaning during my downtime, but I'm just going to relax, So I'm looking forward to that. That's going to be good. This weekend's going to be a good weekend. Get to do some photography and actually have some, not running around like crazy downtime. So that'll be nice.
Projects like building your own cluster computer are easily affordable when you have sound financial planning.
Lucas Casares is a fee-only certified financial planner. He owns and runs Level Up Financial Planning virtually out of Fort Collins, Colorado.
Just like us here at CDP, he focuses on helping you not only establish a real plan, but also to take action on that plan so that you can live your best life.
When it comes to investing in a financial planning service, that really boils down to whether or not you can improve your finances through them. With the help of Level Up, the compounding impact of making better financial decisions will easily pay for itself.
Level Up also has a unique pricing model that will help you no matter where you are in your financial journey.
Yeah, and the best thing about this is that Lucas is a fiduciary for his clients. That means that he's not selling you a product. Instead, he's here to help guide you to a better financial solution.
Find more fun resources and learn more at levelupfinancialplanning.com.
High performance computations using a cluster of compute nodes can be exclusively expensive. Even with the various cloud platform as a service options, spinning up a cluster can become cost prohibitive for an individual or an open source or nonprofit project. Raspberry Pis, on the other hand, are inexpensive, fully functioning computing boards that can be combined and used to build their own cluster.
For his term paper in parallel programming, his graduate course, Beej built a small 4-node cluster using the most recent, as of 2021, Raspberry Pi model. So he's using the Raspberry Pi 4 Model B, which has 8 gigs of RAM and a 1.5 gigahertz quad-core ARM processor. After building the Raspberry Pi cluster, he compared it to 4 nodes of a larger, more expensive university cluster. For testing the clusters, Beej modified an MD5 hash cracking algorithm to use a hybrid model of parallelism combining MPI and OpenMP. He tested clusters at 2, 3, and 4 nodes each, tested with 1 to 4 threads per cluster using hash strings of 4, 5, and 6 character length.
Yeah, and we're going to break that down. That is straight out of the abstracts for the paper. And so we're going to talk about each one of those steps in the episode. Both the Raspberry Pi cluster and the university cluster showed similar behavior when comparing string sizes across the different node and thread combinations. In tests with fewer nodes per cluster, the more powerful university cluster outperformed the Raspberry Pi. However, as more nodes were added, the Raspberry Pi showed similar speeds to the university cluster, even outperforming in a few places, which was a really neat finding.
In this episode, we're going to have some fun going through what Beej did in his project. We'll start with a bit of background about cluster computing and parallel programming. Then we'll look specifically at the program Beej used and how he tested his Raspberry Pi cluster. Finally, we'll talk about the results and some lessons learned while working on the project.
So, starting off, background information. Honestly, guys, each one of these points under this could be its own episode or multiple episodes.
You could do multiple episodes concurrently, for that matter.
And there's a strong possibility that we will eventually get to creating episodes on all of these. They're going into the backlog, along with quite a few other topics I got from the course. So this particular episode, well, I pretty much used the outline for writing my paper. And if I can, I'm going to try to post a link to the paper on there, or just put the PDF of it up on the website so that you guys can actually download that and take a look at the paper that I wrote. It's not academic journal quality, in my opinion, but I got 100 on it for the class, so that's a step in the right direction. So first off, we're going to talk about cluster computing.
Cluster computing involves distributing computational workload across a group of 2 or more interconnected computers. Each connected computer or node in the cluster is an independent, self-contained system that may contain a single or multi-processor core.
Yeah, so with the Raspberry Pis, they had the quad core. So I had 4 Raspberry Pis, each with a 4-core processor.
Okay, so is that like virtual cores or like physical?
Physical. These are physical cores. The 4B does not have virtual, so there's no threads. So I was looking into that because I was thinking if there's like say 2 threads per core, then I mean you got a pretty powerful machine here.
Yeah. Well, it's always important to ask because it's kind of it can be a little hard to grasp because of things like the virtual core type setups.
Yeah.
it gets complex very quickly.
Mm-hmm. Now, within this structure, a node can function as a complete computer containing its own operating system, memory, and input-output drivers. Typically, clusters use distributed memory, as each node in the cluster has its own memory, though the internal architecture may vary from node to node as to how memory is shared between cores in a multi-processor node. It's also possible to mimic shared memory in a cluster using a distributed shared memory architecture.
And I would imagine if you do that, you have to deal with a lot more latency than with system memory.
Yeah, it's actually easier depending on what structure you're using, but it's easier for a lot of things to have the same program loaded on all of the nodes and have each node running it independently and then being controlled by a control node, which is the structure that I did. We'll get into that in the next section, though, in the aftercast too. In the aftercast, we're going to talk about the actual building of it and setting it up. So it'll be fun. Those guys are going to love it. So,
in addition to the compute nodes, and depending on the architecture, you may have a control node. The cluster will also contain a network switch to allow for internode communication. Nodes will also need a scheduling application such as MPI, a message processing interface.
Yeah. There's quite a few of the different scheduling applications. MPI is actually a specification, so it's not a specific implementation. There are multiple implementations. For this, I used OpenMP. No, not OpenMP. OpenMPI. OpenMP is something completely different that we will talk about 2 points from now. It gets confusing because you have OpenMP and OpenMPI. So yeah, it was quite interesting. The thing with clusters is they allow for high performance and high availability without the higher cost of such a powerful single system. They also add redundancy and safety from failure as they can be configured to survive the failure of an individual node. And we're going to talk about that in a little bit when we talk about the different methods for controlling the nodes.
Just out of curiosity, how do things like power utilization, heat sinking, those kind of things, do those compare favorably as well, typically? Or?
Yes. Actually, one of the articles I reviewed talked about power consumption of a Raspberry Pi cluster. And we'll get into that in a little bit, but they had, I think, a 25 node cluster that used about a quarter of the power of a similar university cluster. So, but it didn't have quite as much. It wasn't as powerful. I think it was like only 15 gigaflops.
I mean, I guess that's part of the deal too, is like if you have a load that, is heavy and it's split up between those machines, you probably get through it faster in a lot of cases anyway. So it's measuring the power consumption may be a little bit tricky.
Yeah. So what they did, and we don't actually talk about this in the outline, so I can go ahead and tell you without ruining anything later on. But what they did was they installed power monitoring software on each of the Pis in the cluster. And then they had all of they kind of used I think they're using Slurm. I'm not sure, but basically they used the backbone for the cluster to compile all of that data on the control node. And so they could, like when they ran, their benchmarking was vector multiplication or matrix multiplication, vectors in C++. But, so they were running that. And when that ran, it also ran the power check. And so they were able to actually see the power consumption for each node and the overall power consumption for the whole cluster. So it was actually a really, really well done paper. Kind of fascinating. Actually, I printed it out because it was so good. I'm like, I want that for later because I might, look into doing something similar to that, further on in my graduate career. There's a lot of really cool ideas that I ran across while researching this. My professor was extremely excited about it when I told him what I was wanting to do. And so he pointed me to a lot of things. And he's actually the one who suggested I use, because I was going to do vector multiplication for mine too, for my benchmarking. But he's the one who suggested I use the MP5 hash. And I went out and found the code that I used as sort of the base for it. And we'll talk about that in the lessons learned too, because there's some ways I could have done that better. And there's some pitfalls to the way it was set up that we'll talk about. You'll see when we get into it and we talk about the results and stuff. So next, we're going to jump into a little background and some information about the message passing interface, or MPI. This is a committee-developed specification for message passing library interfaces. It was created by a group of vendors, specialists, and library developers working together on the MPI forum.
MPI is not a language implementation or particular set of libraries for passing messages. Instead, it is a specification with multiple implementations, including OpenMPI and MPICH, among others.
Yeah. So OpenMPI, this is the one that I used, is an open source project running on many of the top 500 supercomputers. And there is a whole nother episode or set of episodes to talk about the supercomputers, because that would be super fun to jump into that, especially if we could get someone on here who knows about
Uses them.
Yeah. And so it combines three of the most popular MPI implementations. FT-MPI, which was developed locally here at the University of Tennessee, LA-MPI, which I think was at the University of Los Angeles, maybe, and LAM/MPI, which I think was University of Indiana and University of some foreign university. I don't remember the exact name. It started with an S. This stuff, that information isn't in the outline. It's my memory from writing the paper.
I was wondering, I was like, am I just not looking at it right? Okay.
Yeah. No. I started reading it and the FT-MPI memory came back. And I was like, oh, hey, that was, a couple hours away over at UTK. And so I was like, yeah, hey. And the other one, I'm pretty sure that was Los Angeles. And I know the last one was Indiana, but they were also with another university and I couldn't remember the name of it. It combines not only those three, but features of those three were very prominent when developing this open source project.
MPICH is another popular open source implementation of MPI, which focuses on variations of Unix operating systems, including Mac OS X, though it does also work with Microsoft's MS MPI.
Works well in multiple environments, Linux or Unix-based environments and DOS-based environments. So that's one of the really cool things about the MPICH. The specification deals with passing information between processes within parallel programming with the goal of creating a standard for improving the ease of use for passing messages and the ability to move code between cluster architectures.
The standard is designed to be used with the Fortran and C languages, but can also be used by C++ by accessing the bindings for C. Not limited by architecture, it can be used with shared or distributed memory clusters and with high-performance multiple core processors.
Now, the really neat thing about this that I discovered after writing the paper was that libraries or bindings also exist to extend MPI into other languages. So for the paper, I was focused on C and C++ because that's what we're using in class. But when I started working on this outline, it's like, all right, I just need a little bit of filler information, stuff that really didn't apply to the paper, but that's going to be more make it more interesting for you guys. And that's when I found out that there are these bindings for other languages like .NET, Common Language Infrastructure, or the CLI. So all of your .NET languages can use MPI. Python, MATLAB, R, and OCaml, just to name a few. And not to leave you guys out, there have been a few unofficial attempts to port MPI to Java, but there is no official MPI for Java.
It's kind of surprising that we have something that they don't. It's usually the other way around.
I know. I think it's because MPICH, Microsoft's MS MPI, was built on that or from that. And so I think that's why we have it.
Yeah, because that's an unusual situation.
I know, right? It's kind of cool.
Yeah, for once.
For once.
Yeah. Now, let's talk about OpenMP, and not to confuse you, between that and OpenMPI. OpenMP was designed for Fortran, but it also extends the C and C++ languages by way of compiler directives and callable runtime libraries. OpenMP allows for multi-threaded programming, allowing a node to use multiple cores and threads on each core.
Yeah, so what we were talking about earlier with the Raspberry Pi, it has 4 cores, but only 1 thread per core. With OpenMP, with MPI or OpenMPI, I was able to connect the 4 Raspberry Pis. With OpenMP, I was able to use all 4 cores on each of the workers. It gets tricky because there's ways to use OpenMP across nodes, but there's a whole paper on it. I'm looking at it right now because it was one that was really fascinating because they had like a lot of really cool stuff in that paper. And there's going to be a link to that one in the show notes, I believe. Another cool thing, OpenMP is compiler agnostic, allowing it to be used in a variety of instances where shared memory parallelism is used, specifically when that is a shared memory architecture. So like with each of the Raspberry Pis, the cores all share the same memory. And so OpenMP works really well with that. That's why I chose that to do that hybrid model.
OpenMP is considered easier to use in shared memory systems, such as compute nodes with multi-core processors, than implementations of the message processing interface.
So it's easier to actually use that on multiple cores, especially when you have multiple threads per core.
Right.
It's easier to use OpenMP than to try to get MPI to work with that.
Well, because I would imagine there's some kind of something that's assuming a network connection that's leaving the box in.
Yeah, I mean that's the default, and so you have to it takes more setup, and your send and receive gets more complicated when you do that. And OpenMP handles a lot of the communication between nodes for you, or not nodes, but between threads.
Right.
Now, going beyond shared memory parallelism, OpenMP has shown to be useful in distributed memory systems as well. Researchers at Purdue University School of Electrical and Computer Engineering described 2 different techniques for use of OpenMP in distributed memory parallel computing. And this is the article I was talking about earlier, that I said that I'm like literally looking at because I printed it out. It was really cool. And I kind of want to play with some of the stuff that they had in there. It got a lot deeper than what I did. But I will say this, my professor told me after reading my paper, he was like, I can't wait for like school to be out. So this summer I can run this on my Pi cluster and compare it to what you got on yours. Because he has an older cluster, I think Raspberry Pi 3s.
Okay.
Which they're also quad core, but not quite as fast. And so he was like, I want to run this on mine to see if it compares to yours, especially the areas where the Pi cluster did better than the university cluster of the same size. So yeah, like that was kind of cool. So going back to this research article, in the first technique, they showed a compile time runtime combination for use of OpenMP with software distributed shared memory systems to proactively move data between the systems. So as numbers were being crunched, they used the software distributed shared memory to go ahead and move the data so that OpenMP could focus on running on the multiple cores, and then the other could send that back to the control node. In the second technique, they translated OpenMP directly to MPI. In both cases, they found the performance of OpenMP to improve the distributed systems. So by adding OpenMP to the distributed systems, they found that it improved the speed by opening up more.
Yeah, that sounds like one of those things where there's an assumed communication barrier.
Yeah.
That is probably getting in the way, because I've run into that with like having processes on the same machine and having them talk over HTTP on the same box. And, as opposed to using like IPC or, named pipes or whatever, it makes a difference. It's like, hey, this can go to multiple, but if it's on the same box, it's not going to be as good. So I understand the reasoning there. Given that, let's talk about other forms of node communication. In addition to OpenMP and specific implementations of the MPI specification, other forms of parallel processing communication exist.
One of the original, older than MPI, is Parallel Virtual Machine. It was created here in Tennessee at Oak Ridge in 1989 for use with C, C++, and Fortran.
Unlike MPI, it does have an actual concrete implementation. PVM uses a set of libraries that allow each node in a cluster to become a parallel virtual machine, meaning that each node must have all the resources.
Yeah. So with MPI, each of the worker nodes only has to have the code that it needs to run what it's doing. But with PVM, they're each full virtual machines, so it needs the full set of libraries, everything that's being used by the whole program.
There's probably a useful metaphor between that and like RAID that I could probably cook up, but not on the fly.
So another one that I used in this, and we used it at school too in the class, was Slurm, not to be confused with the COLA. And that stands for Simple Linux Utility for Resource Management. And by the look on Will's face, I can tell he did not watch Futurama when we were younger.
Never seen a full episode of it.
Oh man, you really should. It's one of those, they planned it out so that there's some time travel that happens in the show. And if you go back and watch the first episode, you can see shadows from where they time traveled back to then in the like last season. For a cartoon, that is cool.
That's an appropriate level of nerdery. I'll have to say that.
Well, I mean, it was I think it was the guys that did at least one of the guys that did The Simpsons.
Speaking of shows I've never seen a full episode of, I don't think.
For real?
I think I have, no.
Oh wow. I haven't quite seen every single episode, but you know, that was one of the shows that I wasn't allowed to watch as a kid, so of course I watched it.
My sister hogged the TV, so yeah, if she wasn't watching something, I didn't get to really. I was outside most of the time.
Fair enough. So back to Slurm. It's an open source workload manager used for scheduling tasks across multiple nodes. And the cool thing about this is the workload manager for a majority of the top 500 supercomputers. So you might be wondering why so many open source and free software on these supercomputers. A lot of them are at universities or research centers.
Well, and I think too, if you've got people that have the wherewithal to run a supercomputer, they have the wherewithal to write the software for the computer. Just, by default.
Well, and a lot of these were written by those people and made open source.
Yeah. I mean, you're basically, it's like an Italian grandmother is going to have an opinion on tomato sauce. Like, it's part of it.
So Slurm creates a workload management with no single point of failure or fault-tolerant job options, which is really cool.
Yeah, it's designed for high performance and scalability as well as resource management so that idle nodes can be powered down when they're not in use.
Yeah. Now, the SunGrid engine is another form of communication that enables execution of shell scripts or Unix batch jobs on a cluster of nodes. The jobs are scheduled to run when the node is idle or under light load. So it's kind of cool. It's sort of a background process for multiple computers. So you can run stuff in the background when the nodes aren't being used, and it controls that. So now we're going to hop into comparing the clusters. We'll talk about each of the clusters as well as testing them and like the test code and what I used for testing them.
And obviously the one we're going to start with is the one that you used, which was the Raspberry Pi cluster. This is inexpensive yet powerful. It was introduced in 2012, and the Raspberry Pi has grown from a single core processor working with 256 megabytes of SD RAM to the current quad core, which is the Raspberry Pi 4 Model B, with options ranging from 2 gigabytes to 8 gigabytes of RAM.
No, the Raspberry Pi 3 was also quad core. Researchers in the Electrical and Computer Engineering Department at the University of Maine found it possible to build a low-cost, power-efficient cluster with 25 Raspberry Pis that is capable of 15 gigaflops of performance using not the quad-core 4 or 3, but the Raspberry Pi 2 Model B nodes.
Wow.
So yeah, that was really cool. That I've talked about this paper a little bit already, but I ran into some really neat stuff. And it's kind of cool because I've got access to all these papers because of being in school. So you have like that university access. So I don't have to just read the abstract. I can actually read the whole paper. It's cool, guys. It really is. Let me just say, if you're not in school, it's almost worth it to buy a year membership to one of these places where you can get the papers, because oh my goodness, there's some really cool stuff people are doing out there, like beyond what's in like Magpie, which if you don't know, that's the Raspberry Pi's easy.
Yeah, I did actually know that. BJ used 4 CanaKit Raspberry Pi 4 Model Bs, that's the 8 gigabyte model, basic kits to create the cluster. The Raspberry Pi 4 Model B contains a 1.5 gigahertz 64-bit quad-core ARM v7 CPU, 8 gigabyte LPDDR4-3200 SD RAM, gigabit Ethernet, 2 USB 3.0 ports, 2 USB 2.0 ports, and 2 micro HDMI ports.
So I connected each of the Raspberry Pis to Zyxel. I honestly don't know how to pronounce it. It's Zyxel GS 1200-5 5-port gigabit managed switch using 3-foot Cat6 cables. Now, the GS 1200-5 is a managed switch with fanless design for quieter running. It has a capacity up to 10 gigabits per second with a 128 kilobyte packet buffer. So yeah, it was cool. It was cool. Now the university cluster, a bit different. In my paper, I compared my Pi cluster to the Tessine 117 or TS cluster at the University of Tennessee, Chattanooga's Sim Center. The Tessine cluster has 33 compute nodes of Dell R730s with 128 gigabytes of RAM and 28 cores each. It has options for Slurm, OpenMPI, and the SunGrid scheduler.
And for testing, Beej used modules containing OpenMPI, GCC with C++ 17, and MPI exec.
Speaking of testing, let's go ahead and jump into talking about how I tested the clusters. They were tested using a brute force MD5 hash cracking program written in C++. Now, I found the original code on GitHub, and that will be linked in the show notes, along with my modifications. So that original code used OpenMPI to spread the work of creating and comparing hashes of every string possible using only lowercase characters and knowing the length of the original string. So it's like, this is not written to crack passwords. It was written to
crack really bad passwords.
Really bad passwords when you know the exact length of the password and it's only lowercase characters. This was designed to test performance. Because it had already built into it timers.
Oh, you said that the Raspbian Buster Lite OS couldn't connect to GitHub. Did you ever figure out why that was?
No, I did not. My professor looked into it. We tried a bunch of different stuff. I even talked to a friend of mine who just graduated from grad school at MTSU and had him look into it. And none of us could figure out why. The only thing is, my professor was thinking that possibly this particular, the ARM structure, architecture for the Pi 4 isn't as well used. And so I may have been missing some of the core operating system components that I needed to make that connection, which was weird because I couldn't even ping github.com.
Was that, were you trying to connect you said a ping wouldn't work?
Yeah, I couldn't even ping it.
That's kind of strange. I would think it would be like some kind of HTTPS, certificate, validation thing.
Wow. I have no idea. But I was able to clone the repo, and then I uploaded my changes to Bitbucket. And I could access Bitbucket from my Raspberry Pi cluster from the control node. So that's what I did. Yeah.
Yeah. Sometimes you have to do stuff like that.
Yeah, straight up. That just, it's what worked. And so I put it there, and then I could pull it down onto the control node. And then, so what I should have done was use Slurm to send, compile it on the main one and then use Slurm to send it to all the other nodes. I didn't think about that until towards the end of the project. So I'd used Slurm to put other stuff on there when I was setting them up, but I didn't think about using it for that. So I actually wrote a script that basically put it onto a file share flash drive, and then SSH'd into each node, copied that, then went to the next one. It worked.
Yeah, that's, I've done some code here lately that it's like, you know what? I wouldn't release this into production, but I want this done.
Yeah. That was kind of the thing. I was like, I just got to get this. I copied it manually one time, and I'm like, this is dumb. I can write a script to do this. What I didn't think about was, hey, 2 days ago, actually by this point in time, it was about 2 weeks before, because I had a lot of trouble with the code stuff. But anyway, it was like 2 weeks ago, I used Slurm to send everything out. Why didn't I think to do that? I don't know. Anyway, so on with testing the code. So within the code, MPI was set up to work with one control node and n-1 worker nodes, where n was the total number of nodes. So in the case of my cluster, 4 nodes, so n equals 4. I had one control node and 3 worker nodes.
Okay. So the code first calculated the total number of strings possible based on the number of characters in the string. Then it divides that by the number of nodes in the cluster.
Yeah. So each node is sent a starting point to generate strings of the correct length. And the generation is kind of interesting because you have 26 characters. So it takes, you have 26 possible characters. It takes and creates an array of however long the password is. So if it's 4 characters, it creates a 4-character array and then populates it with the letter A. Then it starts at the last
and loops it
character, and it goes, all right, take the mod of where we are and divide it, or take the mod of where we are and 26, the number of characters, and then find that find which character that relates to in this array of, use the index of the array of A through Z lowercase to find that. That's that character. Then divide by that, take the next mod, and go down.
Okay, so if you do that, that's going to interleave the way that it picks them up, right? So one node gets, all A's, the next node gets all A's and the B?
No. So let's say you have 4 characters with 26 possibilities each. So 4 to the power of 26. That's not right. I think I got that backwards. I think it's 26 options. Yeah, 26 options to the power of 4. Yeah, that's how that works. So with a 4-character node, you have 456,000, round up 457,000 possibilities. We'll just round off and say you have 300,000 possibilities. You send the numbers 0 as the begin and 100,000 to worker node 1. You send 101 or 100,001 as the begin and 200,000 to worker node 2, and so forth. So you divide it up like that. And then to get the password, it took so you know what the mod function does? It gives you the remainder. Yeah. So it took the remainder of whatever, so it would start with 200,001, and it would create a word from that number. And so starting with the last character, it would go, all right, take that number, mod the total number of characters, 26. Whatever the remainder was there, it's going to be less than 26. It would figure out which letter in the, using that as the index, which letter in the array of numbers or of characters, A through Z, that was. So let's say, it was H. So the last character there is H. And then you would go and you would divide, you'd reset that number to, you would reset it to divide by 26. Now, whatever the integer when you divide by 26 is,
not the remainder,
now becomes your new.
Okay, I got you.
Yeah.
All right. I was kind of wondering how they split the workloads, because I was like, you surely aren't generating that whole thing and then pitching it over the wire. It's like, oh no, you're just giving it the marker points so that it can figure it out.
Yeah, exactly.
Okay.
And so what I did was I added OpenMP to the code that once you send, so MPI would send, say, 200,001 to 300,000 to the last node. Well, OpenMP would then go, hey, that is 100,000 possibilities. There's 4 cores. Each core gets 25,000 possibilities and runs it. So for each node, I sped up the process by a factor of 4, roughly. And then I tested to see, did it actually speed it up by that much, because you have other things in the mix. So going into that cluster testing, each cluster ran 216 tests. Out of those, there were 36 tests for each of 6 different hashes. So I had 6 different words that I hashed that I was trying to crack. And I did 36 tests for each one of those words. In order to see a difference in the load between clusters, I hashed different size strings, ranging from 4 characters to 6 characters. Now, because of the nature of the brute force hash cracking, different strings of the same size took different amounts of time to be cracked. So, for example, the 2 that I used for 4 were tongue, T-U-N-G, which was the last name of the original author of the MD5 hash cracking code. And he used his last name in his example. So I just was like, hey,
Okay.
and then the other word was bird, B-I-R-D. And so if you can imagine, given the way that I described it, bird took a lot less time to crack than tongue, T-U-N-G, because of where it fell in. So like bird was towards the beginning of those possibilities, where tongue was like right in the middle. Because if it had been towards the end, the last node would have caught it. But it was like in the middle of one of the nodes.
Oh, okay. Yeah, because you subdivided it and it's in the middle of the set.
Yeah.
So it's sort of like performance on like quicksort or something like that. Like,
yeah,
or not quicksort, like a binary tree. I can't remember the name of the algorithm where you slice an array in half, like a binary search. If it's if it's in the right place, it takes longer.
So, and then the results were taken from averages of these tests. So basically, I had 2 4-character strings, tongue and bird, 2 5-character strings, Mandy and Burns. You can guess where I got those. And 2 6-character strings, Amanda and OpenMP.
Also can guess where you got those.
yeah. And I did that so that I could get the idea was to get one that took a long time and one that didn't take as long, so I could get kind of an average. Speaking of results, overall performance-wise, created 216 lines of data, because like each test produced a line of data, and put those into a CSV file. Basically, as it ran, I have a script that ran all the tests and just tossed them into a CSV file that I could then open up and use for my data. Which don't think ill of me. I used Excel to process my data, because by the time I got it all working, I only had like a day or 2 left before the paper was due. And I'm like, I don't have time to run statistical analysis on this.
Yeah.
And I also realized that I didn't have enough data, and we'll talk a little bit more about that later. Like, I realized some stuff about the data that I'm like, if I had another week, I would rerun this and have a lot better view of what's going on. But this gave me kind of a good overview. So I took the 3 tests for each hash. So like, I tested each hash based on a node thread combination. So like 1 node, 1 thread, 1 node, 2 thread, 1 node, 3 thread, 1 node, 4 thread, then 2 node, 1 thread, 2 node, 2 thread. You see where I'm going with this. And so I took all of that and I combined it together to create 36 averages, 1 for each combination of character length, number of compute nodes, and number of threads per node. Overall, the speed averaged kind of about as expected. Fewer nodes and threads performed slower, whereas the more nodes and threads you added, the faster it got. The 6-character strings, though, created a kind of on both clusters, created this W shape when I plotted them onto a graph. And I think that's because the method of splitting the potential strings that we talked about earlier between nodes, just the 2-node, 3-thread cluster caused the correct string to be placed further from the entry point. So it like took a lot longer for that one than any of the others. So like you have this high, goes down, pops back up, goes down, pops back up. And so like I think those there's like 2 combinations there that cause it to spike back up in time. And it's because of just where it was placed when it was broken down. Another spike could be seen from the 4 threads in the smaller set of nodes to the 1 thread in the larger set of nodes. Like, those are kind of similar. So when you had 1 node with 4 threads versus 1 thread with 4 nodes, or with 4 nodes with 1 thread, basically.
Yeah, because that changes the growth rate of the search.
Yeah.
Okay. That makes sense. It takes a minute to turn that over in your head.
Yeah, it really does. It really does. So the other thing I looked at was the average speed per node by the string size. So I compared those speeds and this was just on the Raspberry Pi cluster, based on the number of characters in the string. The 4-character hash performed about as expected, showing an increase in speed with the increase in number of threads. However, 2-node clusters for both 5 and 6 character string hashes showed like varying results. Like when you had 2 nodes, it was just like, it was weird. And again, I think this is part of just the way that the code split up the possibilities. Finally, I compared the Raspberry Pi with the university computer cluster. And that was interesting because at the smaller levels, the university cluster just way outperformed, like massive difference. But when you add more nodes, it kind of leveled out. And even in a couple of places, the Raspberry Pi outperformed the university cluster.
Yeah, especially if you evaluate it based on the actual like electricity used, those kind of things. I could see that being.
Well, I didn't do that, but yeah, that would be an interesting thing to do too. So a couple of lessons learned. First off, hash cracking may not be the best measure. Brute force hash cracking, while fascinating, is probably not the best test of performance just because what I was testing. Like if I was testing, all right, the same stuff across it, like the same number of nodes, the same number of threads, then yeah, that would have been fine. But because the way it was breaking it down was different between them, it didn't quite give me the kind of information I wanted. Because the speed of the speed of finding the hash depended kind of on where in the set, that was generated based on the number. So yeah, matrix multiplication or actual benchmark testing probably would have been a little bit more consistent, but maybe not as much fun.
You should have just tried to mine Bitcoin on their supercomputer. I'm sure somebody's done that.
Oh, they've got stuff to prevent you from doing that, I'm sure, because that they have a cluster of GPUs that I had to use for one of the projects in class. So yeah. The other thing is that for true statistical analysis, I need more data. So, a better design for testing would be to use a larger, like more hashed strings and calculate the speed differences between no parallelism and running each of the node thread like combinations. So like, all right, how long does it take to hash this compared to like, how long does it take to hash it with, or to get the hash without, any parallelism? One computer, one node, or one node, one thread versus these others. Then do a bunch of those and like analyze the statistics there. More tests per node thread combination and fewer different hashes would also allow for better sets of data. Basically, I needed more tests, even though I had a bunch of them. They were all too varied. So
right.
I would need a lot more data from similar tests, but I was going for more of an overview. So I got what I wanted. It's just for a better statistical analysis, I would need that. Now, guys, I really enjoyed building and testing the Raspberry Pi cluster. It's an example of some of the fun things that we get to do when learning in the field. It did turn out to be a little bit more expensive than expected. This episode turned out to be a little bit longer than expected. We kind of had a lot of fun with it. A lot of this had to do with me choosing to use the 8 gigabyte Pi 4. And I did that because I kind of want to reuse those to build some stuff this summer. I could have saved money and still accomplished the hybrid parallelization using less RAM or even the Raspberry Pi 3. Now, whether you want to build the best or save money, you can use the information in the episode as an example of some of the fun things that we get to do as programmers. If building a cluster computer or playing with the Raspberry Pi doesn't inspire you, then find something that does to help you find joy in learning within the field. Now, if you did find this fascinating, check out the Aftercast, where we'll talk about actually building and implementing the cluster, which is going to be even more fun. That pretty much wraps us up. Before we close everything out, Will, what do you have for us this week for Tricks of the Trade?
Well, I'm going to make this quick since this was a little bit longer episode than normal, because it's really more of an exercise for people to get into versus me telling you something. Notice how much of the stuff Beej dealt with coordinating interaction between multiple machines, how much that applies when you have to deal with teams of people, right? Because if Beej had one Raspberry Pi 3 and a couple of 4s and a 2, the way that he split his workload up and had to deal with things would have been very different. Similarly, the way that he ran into issues as far as quantifying, statistically, which was a more efficient setup, you're going to run into the same thing in tech, because most of the time when people say that they're comparing the same thing, they're actually comparing situations that are completely disparate in a very, very similar way. I think, while the parallel computing is neat in its own right, if you kind of take a meta approach and you look at it and you go, okay, is there something mathematical or statistical or just process oriented here that informs regular life with a team of programmers? I think you're going to find a lot of good stuff. So I suggest you look. And that's all I got.
Stand by for Titanfall.
If you have a question or comment, please email us at neckbeards@completedeveloperpodcast.com. Our theme music is an excerpt from Stand By for Titanfall by Pure Bells, available on SoundCloud and licensed through Creative Commons.
For references, show notes, and extra tips and insights, be sure to check out the website at completedeveloperpodcast.com. Help us make the show possible by supporting us on Patreon at patreon.com/completedeveloperpodcast. You'll get extras, including a weekly aftercast where we discuss the topic of the week and bonus material with some of our patrons.
You can also follow us on Twitter at CompleteDevPod, like our page on Facebook, and follow us on Instagram to keep up with news about the show. Join the conversation anytime via Slack by signing up at slack.completedevelopernetwork.com. Thanks for listening. See you next time.